This is Dane Quinn from the University of Akron, and for today's video lecture, I really want to talk about the acceleration equations for mechanisms. Now, we'll start, as we always start, with the loop closure equation, right? And if you remember, this is actually kind of the same way I started the velocity equations. The loop closure equation describes the essential kinematics, including all the constraints, and because it's valid at any time, then we can start taking derivatives. We took the derivative once and determined the velocity equation, which in a sense implies that the change in the components of a loop closure equation have to be consistent. So now, for the acceleration equations, you can probably guess what we'll do. We'll take the derivative of the velocity equations, which were the derivative of the loop closure equations. If you went back and looked at the acceleration lecture, we saw and we kind of know that acceleration is the second derivative of position or the first derivative of velocity. And so the acceleration equations essentially represent the second derivative of the loop closure equation or the derivative of the velocity equation. So again, here we have a mechanism. It's a simple slider crank. We have a link 2 from O2 to A, and that's connected to a link 3 from A to B. And then a sliding element that moves along a line of action that essentially passes through O2 and is horizontal. So you probably know at this point, but I'll go ahead and do it anyway. The loop closure equation is the vector from O2 to A plus the vector from A to B equals the vector from O2 to B. So really, here it is, the vector from O2 to A plus the vector from A to B, or B with respect to A, is the position of B with respect to O2. Now, of course, we need to specify this a little bit, so let's go through and define some coordinates and directions, that kind of thing. We have I and J fixed in the ground, and we'll define I2 and J2 to be fixed in link 2, and of course oriented with an angle theta 2. And then we'll define I3 and J3 to be fixed in link 3, and then they are oriented with an angle of theta 3. Notice that theta 3 is also this angle, while theta 2 represents that angle for the bases. Finally, the vector from O2 to B changes magnitude. Of course, it's in a fixed direction, I. But we need to know what that magnitude is, right? Or at least we need to define a variable that describes it, and we'll call that x. So, again, we've seen lots of slider cranks, but here it is again. X describes the length of the vector from O2 to B. Theta 2 describes the orientation of link 2, and theta 3 describes the clockwise orientation of link 3. So our loop closure equation is L2 in the I2 direction plus L3 in the I3 direction equals X in the I direction. Right, so again, this is the position equation. Now, if I want to calculate the velocity, I'll take this equation and apply a derivative to everything. Right? And so we end up with the derivative of L2 I2 plus the derivative of L3 I3 equals the derivative of x in the I direction. So now we'll use the product rule together with our description of how directions change. And for that, we need the angular velocity of link 2, which in this case is theta 2 dot in the k direction. We also need the angular velocity of link 3, which is now minus theta 3 dot in the k direction. Remember, theta 2 is positive counterclockwise, right? So if theta 2 dot is positive, this is rotating in the plus k direction, which is out of the plane. If theta 3 dot is positive, though, it's rotating clockwise, which of course is the minus k direction. So, as a result, we can go through this and determine the velocity equations. I'm not going to go through this in great detail, right, because we've done this a lot, right? But maybe pause the video, work through this. The derivative of I2 is omega 2 cross I2, right? So that becomes L2 theta 2 dot in the J2 direction. Here, again, because theta 3 is defined the way it is, we end up with minus L3 theta 3 dot in the J3 direction. And here, of course, x changes, right? So I get x dot I, but then the direction I is fixed. So now we have our position equation, right? Or our loop closure equation. And we have just obtained the velocity equations. Again, now we want to go and determine the acceleration equations by taking a derivative of this. So here it is again. I've rewritten the loop closure equation, or the position equation, and the velocity equations. So now for this mechanism, I'd like to take a derivative of the velocity equations, right? So really, that is this equation, right, that will evaluate the change in all of these components. Because the loop closure equation is valid for all time, well, then the change in the loop closure equation has to provide the velocity equations, and then the change in that will provide the acceleration equations. So now let's just look at one of these terms, right? Let's look at L2 theta 2 dot in the J2 direction. This term is going to be similar, and then this term is pretty easy, right? We just take another derivative of x dot, right? But here, we'll take the derivative of the magnitude, and here the magnitude is L2 theta 2 dot, and this is a scalar quantity in the J2 direction, plus L2 theta 2 dot times the derivative of the direction, J2. This is simply the product rule. Now, looking at this first term, L2 is constant, but theta 2 dot could potentially change. So, we end up with the derivative of theta 2 dot in the J2 direction. And now, for this second piece, well, go back to our vector derivatives. This is the angular velocity of link 2 cross J2. Next step, well, the derivative of the velocity, well, that's going to be the second derivative. So we'll just write this as L2 theta 2 double dot in the J2 direction. And then L2 theta 2 dot. And the angular velocity is theta 2 dot in the K direction cross J2. So finally, we have the following. K cross J2, well, that's minus I2. Notice that I have two theta 2 dots. So in the I2 direction, I get minus L2 theta 2 dot squared from this term, and then plus L2 theta 2 double dot in the J2 direction. So this is the derivative of this first term. Now, we can do the second term, right? And finally, we can do the right-hand side, which is just x double dot in the I direction. And we find that the acceleration equations end up as, well, we have this first term, minus L2 theta 2 dot squared in the I2 direction, plus L2 theta 2 double dot in the J2 direction. Now we have to calculate the derivative of this second term. You might want to pause the video at this point, work this all out. And when you do, you get minus L3 theta 3 dot squared in the I3 direction, minus L3 theta 3 double dot in the J3 direction. And then finally, the right-hand side is simply x double dot in the I direction. Let's look and see what's new. Theta 2 dot we found from the velocity analysis. These directions were all known from the position analysis. Theta 3 dot is from the velocity analysis. But we've introduced this theta 2 double dot term. Likewise, we've introduced a theta 3 double dot term. And we've introduced x double dot. So now these are our acceleration variables. They are the new quantities that are introduced when we go and calculate the acceleration equations. Notice that the acceleration equation is a vector equation, right? So it has two components. We have three acceleration variables. So to solve for these, we need to know one. You give me one of these quantities, and I will find the other two using, again, the acceleration equations. Typically, we're given theta 2 double dot, and then we would go and find theta 3 double dot and x double dot, the acceleration of the slider. So just kind of a quick summary. The loop closure equation relates the position variables. In this problem, that's theta 2, theta 3, and x. Right? So theta 2 is here in I2 direction. Theta 3 is in the I3 direction, and of course x is right there. Then the velocity equation relates the velocity variables. So we take the derivative of this and we introduce theta 2 dot, theta 3 dot, and x dot as new unknown quantities that need to be determined. So in all of this, one of these position variables is given, one of these velocity variables is given, and of course one of the acceleration variables of theta 2 double dot, theta 3 double dot, and x double dot are given to us in the problem statement. So the idea in finding acceleration is that we want to solve for the position and velocity variables, and then solve the acceleration variables, or solve the acceleration equation for the acceleration variables. This is exactly the same procedure that we went through for velocity. It's now just one more derivative on the loop closure equation. But again, kind of the procedures and the steps that you go through, really very similar, right? So if you think about what we have here, let's imagine that theta 2 double dot is given. And we've already gone through and solved for the position and velocity variables. So that means that all these directions are known, and theta 2 double dot, or theta 2 dot is known, right? So I can write this vector, right? I know this vector because, again, I'm assuming that theta 2 double dot is given. And I can also add up this vector, right? So these three known vectors give me something here, and this represented by this dashed line. And then to that, I must add something in the J3 direction. And ultimately, I have to get something in the I direction. I mean, this is essentially a geometric solution for this vector equation. So here, what is it that I have to add in the J3 direction to get something in the I direction? Well, it's kind of obvious. I'm going to add this vector in the J3 direction so that the resultant is that vector in the I direction. So here, this vector has to be minus L3 theta 3 double dot in the J3 direction. And this vector is x double dot in the I direction. So one of the things that you notice from what I've done here is that this horizontal vector is actually in the minus I direction. So if we were to go and figure out what x double dot was, well, it would have to be negative, right? Because the only way this can be in the minus I direction is if x double dot is negative. Likewise, we would go through and find that theta 3 double dot is also negative, right? Because this vector is in the plus j3 direction, right? But we have this minus sign out front of this term. So the only way to make this term in the plus j3 direction is for theta 3 double dot to be negative. So, right, this geometrical sort of graphical solution can actually give us some useful information really quickly. If you wanted to go and figure out what these variables were, you could maybe measure this vector, but we're actually going to go through and calculate it analytically using our vector acceleration equations. So let's do that. And we want to focus here on solving for these acceleration variables. So I'm going to assume that we've already solved for theta 2, theta 3, and x. So maybe theta 2 was given, and we solved for theta 3 and x. Likewise, I'm going to assume that the velocity variables are also known. Right? So if, for example, theta 2 dot was known, I've already gone and determined theta 3 dot and x dot. So here, I'm going to assume that theta 2 double dot is known, and I want to find the remaining acceleration variables. So theta 3 double dot and x double dot. And these will all be done in terms of these position and velocity variables. So in particular, let's start off and find theta 3 double dot. Well, we have our vector loop closure equation. So if I want to solve for theta 3 double dot, really the way to think about that is to eliminate x double dot from this vector loop closure equation. So the way to do that is to dot with a perpendicular direction, right? So here we have minus L2 theta 2 dot squared in the I2 direction. I'm going to rewrite this acceleration equation. And then the perpendicular direction here is j. So if I can take this equation and dot it with the j direction, then the x double dot term vanishes. One of the nice things about acceleration analyses and solving these things, velocity as well, is that we've already solved for the positions, so all the directions are known. Eliminating unknowns essentially amounts to taking dot products with certain directions, in this case, j. So here, maybe you want to pause the video lecture and go through this, knowing that you can find I2, J2 with respect to I and J, I3 and J3 with respect to I and J, and the result that you get is minus L2 theta 2 dot squared. I2 dot J is sine of theta 2. We have plus L2 theta 2 double dot times cosine of theta 2. I3 dot j actually is minus sine of theta 3. So we end up with plus L3 theta 3 dot squared sine of theta 3 minus L3 theta 3 double dot cosine of theta 3 equals 0. So now I can solve for theta 3 double dot. Theta 3 double dot here equals, well, I'm going to group these things in the following way. Notice that we have two terms that depend on velocities, right? So I'm going to write those together. Minus L2 theta 2 dot squared sine of theta 2 plus L3 theta 3 dot squared sine of theta 3, of course divided by L3 cosine of theta 3 plus, and then now the theta 2 double dot term. So here that ends up as L2 cosine of theta 2 divided by L3 cosine of theta 3 and theta 2 double dot. So notice that I have a term that depends on the velocities, and then I have a term that depends on the input acceleration. So once I know this, I can actually go back to the loop closure equation and maybe use a component. So in particular, the I component to solve for x double dot. Right, so here doing that, we would find that x double dot is equal to, well, I'm just going to take the I component of all of these pieces. Right, so I get minus L2 theta 2 dot squared cosine of theta 2 minus L2 theta 2 double dot sine of theta 2, and then the I component of these two is minus L3 theta 3 dot squared cosine of theta 3 minus L3 theta 3 double dot sine of theta 3. And notice that this acceleration variable was determined previously, while theta 2 double dot is my input acceleration variable. So again, I'm going to solve for theta 3 double dot, and then I'm just going to go back and take the component in the I direction to determine x double dot. But in that, I'll make use of this result that I just found for theta 3 double dot. Okay, so a couple of things about this. Notice that if I want to find the acceleration of a mechanism, or the acceleration variables, then I can't just use the input acceleration. Right? So the acceleration depends on the configuration, right? So the position of the mechanism. Right? We've got a lot of theta 2s and theta 3s here. And it also depends on the velocity. Right? So I've got some theta 2 dots and theta 3 dots. So it depends on the configuration of velocity at an instant. In addition to the input acceleration. Right, so in this case, we took theta 2 double dot as our input acceleration. We said that's known. So we solve for theta 3 double dot and x double dot. Again, just like with velocity, we needed to solve for position first. With acceleration, we need to solve for velocity first, which of course implies that we need to solve for position first. So solve for position, solve for velocity, solve for acceleration. I will note that these output acceleration variables and in this problem that's x double dot and theta 3 double dot. So they depend on the square of the input velocity variables. So, for example, if theta 2 dot is the input, then this acceleration depends on the square of the input. Likewise, theta 3 dot would depend on theta 2 dot, so the fact that we have a square here implies that, again, this term would depend on the square of the input velocity. So that's kind of important, right? Because if I double the input velocity, what happens to the accelerations? Well, they actually go up by a factor of 4. So this has real implications for things like high-speed machinery. Anytime you're concerned with inertial loads, right, so the mass time acceleration terms, those can get really large for high operating speeds, precisely because of the kinematics and the fact that these output accelerations depend on the square of the input velocities. And they are proportional to the input acceleration. You know, another interesting observation here is that even if your input acceleration is 0, right? So if theta 2 double dot is identically equal to 0, that would imply that the operating speed of the input link was constant, for example. So maybe theta 2 dot is rotating at constant speed. Well, in that case, these output accelerations need not be 0. So both theta 3 double dot and x double dot can be non-zero. Right, so you might be inclined to think, well, if I'm inputting a constant speed, right, all of my velocity variables should be constant, all my acceleration variables should be 0. But that's not the case here, right? A constant input speed can still give output accelerations due to the kinematics of this linkage. So let's look at a really quick example, right? Again, here we have our slider crank. I'll take L2 as 40 centimeters, and then L3 here will be 100 centimeters. And at this instant, I'm going to assume that theta 2 is 60 degrees, right? So that's my input position variable. I'm going to assume that theta 2 dot is 12 radians per second. That's my input velocity variable. And I'm going to assume that input speed is constant. So the input acceleration, theta 2 double dot, is actually equal to 0. So, and then let's go and figure out what these output accelerations are. So again, we always start off with a position analysis. Well, if theta 2 is equal to 60 degrees, then looking at the loop closure equation for this linkage, we can solve for theta 3 as 20.27 degrees, and x here is 113.8 centimeters. Now, I'm just kind of go through this. I would urge you to actually stop and do this problem. Pause the video lecture, right? Go get a sheet of paper, pen, a calculator. Go back to the loop closure equation and go through this position analysis. Go back to the velocity equation and figure out theta 3 dot and x dot. And when you do, you'll find the following. So from a velocity analysis, theta 3 dot is L2 cosine of theta 2 divided by L3 cosine of theta 3 times theta 2 dot. So again, using these positions and the lengths and the input velocity, this is 2.558 radians per second. That's what we find. Likewise, we would find that x dot is minus L2 sine of theta 2 times theta 2 dot, and then plus minus L3 sine of theta 3 times theta 3 dot, which actually would be minus 504.3 centimeters per second. So again, this is what we get from a velocity analysis. Finally, at this instant, we can calculate the acceleration. So again, it's at this instant because these are the instantaneous position and velocity variables. And remember, for this problem statement, theta 2 double dot was equal to 0. Then evaluating this expression, we find that theta 3 double dot was minus 50.76 radians per second squared. And finally, x double dot, the acceleration of this block, minus 1,735 centimeters per second squared. So again, I've kind of just given you the answer here. I would strongly encourage you to go through and work this problem out yourself and make sure that you get the same results that we got here. So that's it. That's our introduction to acceleration. It's kind of a lot of the same as before. Same as it ever was. We'll just take the velocity equations and take the derivative to find the acceleration equations. Just like when we determined the velocity equations, we took the loop closure equation and we took a derivative. So that's it. There'll be more to come. We'll do some examples. But this is our introduction to acceleration equations. Thanks a lot. Take care. Bye. I need some coffee.